It's a linking sense, I don't know what that means. Sure, but for consideration of the yeah, that's what it is. Okay.
Wow. That's sick. Yeah, okay. Okay, so I hope you're all here for the Cbor Lightning tutorial. I'm Carsten Bormann. Those slides are at this point here. So it somehow magically turned on. We don't know why it didn't for 5 minutes, but then it somehow did. So in this Lightning tutorial, I want to cover 3 questions. One is, what is Cbor and when might you want it? Second is, how does it work? And the third one, how do you work with it? So let's talk about Cbor. And I'm going to steal some slides from David Crockford here, who was the inventor of JSON. So okay. So 30 years ago or 40 years ago, we were all writing our COBOL programs and generating data formats completely ad hoc. Then we started integrating around databases. And then finally XML came along, and we had a common data format that we used for interchanging information. XML is originally a document format, but it can be used for interchanging data. It's just a little bit remote from what you would want to use. And finally, people came up with interchange formats that are actually based on how programming languages would want to represent data. And this is the thing that JSON finally became the most used instance of. So the JSON format for interchanging data is the basis for a lot of work right now, both in the IETF and generally in the application interoperation environment. Now in the IETF, of course, we do our data formats this way. So there is something called TLVs, type length value representation. And in our RFCs, we write this down in box notation. Box notation because we have all these boxes with various things in them. Okay, this may seem a little bit archaic to some people, but it has served us well. So I'm not trying to belittle this. This actually works reasonably well. The main problem is that every single new protocol comes up with a new TLV format, and you have to write all these protocol parsers, and these protocol parsers have bugs, and they lead to security problems, and so on. So maybe it's time to move on. And the obvious next step is on this slide. So this is how your typical XML document looks like after a few iterations. So you want to specify this, because this, of course, no longer can be reasonably described. So we have another thing called the XML schema language, XSD. And for reasons unknown to mankind, the people who invented this decided to write this down in XML. So it is as unreadable as the XML. There's something called RelaxNG that helps a little bit. Yeah, generally application programmers are not too fond of this. You can make it work. The Java environment helps you with that a lot. There are tools out there and so on and so on. But really, in the last 10 years, people have been converging on the JavaScript object notation JSON. And the idea for JSON was that it is minimal, that it is text-based, and in order to stop all these discussions, when you define a new data format, and there are 2 million people who can do that as well, and they all have an idea how to do this, and they want to do it slightly differently from you. And just to stop these discussions, David Crockford decided to put this as a subset of JavaScript. So he took the object notation of JavaScript and used that as the interchange format. Of course, that helps with acceptance in the JavaScript community, because it's a very natural data format for them. And for everybody else, it just means you don't get a turn at saying, how about changing this comma into a semicolon and putting it in a space there? No, it's all defined in JavaScript. So this was a pretty quick standard to establish. Now, JavaScript has a certain data model. And in JavaScript, you have strings, text strings, numbers, booleans, something that's called objects, which in most other languages are called dictionaries or tables, arrays, and the null value. So that's the data model, and that's the underlying model of behind all JSON data items. So an array in JSON might look like this. Of course, you can have nested arrays. and so on. And a table or called object in JSON might look like this. Who's familiar with JSON in this room? Okay, so it's a pretty well-known format by now. These things are called objects because in JavaScript they are called objects. So for a computer scientist, these are really maps. And that's the term I'm going to use in the next 20 minutes. Now, the nice thing about JSON is you don't need schema information for ingesting this information. You just point a generic parser at the JSON document, and it gives you this structure with arrays, maps, strings, and so on as a programming language object, and you can start working from that right away. And most programming languages have something like Boolean types, number types, string types, a special null value, some form of maps, and some form of arrays. When you define a JSON object, then you often will want to use what is called objects or maps in JSON as structures. So you, like in the example here, you use the names in the map just as indication what the thing on the right side of the colon actually means. So you say width, and then you give a number that is to be interpreted as a width. So this is the typical way in which you do structured information in JSON, but you also can just use arrays and define the meaning of a position in the array, something that I would call record usage. Now, one of the nice things about this is that in a key value structure in this map approach, you can just add new keys by new items by defining new keys. And generally, JSON consuming applications just ignore what they don't understand. So this is a way to do evolution. If you want to put new information into a data format that applications already understand, you just use new key names, and then yeah, the old applications will still work, but of course they won't understand the new information that they didn't know about. Okay, so this is JSON, and JSON is well established, works very well, but it does have its limitations. And that is particularly interesting in the constraint space where we do Internet of Things types of applications. And the biggest problem really is that JSON doesn't have any idea of binary data. Of course not, because it's a text format. So you wouldn't have an easy way to put in binary data. But also, it's really a format that originally was meant for a programming language, not for data interchange. So for instance, all numbers are in decimal. And it is actually surprisingly hard to convert between decimal and binary representations of numbers. Not for integers numbers, that's trivial, but for floating point numbers, it's really an art that has taken about a quarter century until we fully understood it. When you implement something in JSON, then you usually have to do copying because strings use quotes around them, and if there is a quote in a string, you have to do escaping and so on. And well, if you somehow do want to use binary, then you use something like base 64 encoding, and that also requires copying. JSON was deliberately designed not to be extensible. So JSON is JSON. If you do want to have some additional representation types beyond the 7 that I showed, string, number, and so on, the only thing you can do is use something like the structure format that I showed and say date : and then put in your date font. So you cannot add new types at the representation level. You only can add them at the semantic level. Finally, at the implementation level, we know about interoperability issues in JSON. There's a whole RFC that tells you how to use JSON in a way that minimizes interoperability issues. And the ugly thing here is that this reduces the expressibility you have when using JSON. So for a long time, I have used this slide here in my talks about data formats. The XML people actually have at some point defined something called EXI, which is their efficient XML interchange, binary format for sending around XML data. And we just had no idea how to do this in JSON. So over time, JSON is now more than 10 years old. A lot of people have defined their own binary JSONs. And one of them is called BSON. And that's actually the most cited one. If somebody thinks about binary JSON, they are going to say BSON just because the abbreviation is so great, not because the format is so great. The format is really not so great. But BSON is not the only one of those. There are dozens of them. And they all have different objectives. So they're not just trying to do a binary JSON, but they have specific ideas in mind. So for instance, BSON was designed for a specific database, the MongoDB, and its main design feature is that you can update data at rest. So when you have a BSON representation in your database, you might want to increment a number in the middle of that representation. And that, for instance, means BSON cannot really use variable length numbers. It has to use fixed length numbers. So this update in place works. So you see that different requirements, different areas of application lead to different binary JSONs. And again, there are like 20 of them around now. And interestingly, most of them are actually more complex to implement than JSON. You would expect when you go to binary, it's much easier to convert between the binary interchange format and the binary representation within the computer, but that's not the case. These formats are often complex. So when we started looking at data interchange formats in the constraint space, where we might have a microcontroller with something like 128 kilobytes of code, we were thinking about a way to get this simple. Wanted to build something simple and focus on small code size and compact data size. But in this order, the implementation was supposed to be simple, so you can actually implement it in a small number of codes. And my C implementation is 822 bytes of code, not kilobytes, not megabytes, bytes of code on an ARM. So this was one of the objectives here to be useful in the IoT space. So the data size was supposed to be compact, but not with extensive bit fiddling, which would have increased the code size again, but just with a very natural mapping between the internal representation types and the interchange types. So 2 years ago, 3 years ago, we actually started writing this up and came up with something which is called concise binary object representation. How did we get this title? Well, this is JSON, but it's not a notation, it's a representation, so it's object representation. And it's not JavaScript, and the two most important attributes here are it's concise, it's meant to be simple, and so on, and it's binary. So how do you pronounce this? Cbor. Now what is a Cbor? Maybe something like this. Okay, so after we defined this, we can finally fill in this field in the table. So more specifically, the design goals were being able to encode all the data that we actually use in IoT and generally in IETF protocols. Make a compact implementation possible. That's the code size thing. Being able to parse without a schema description, that's the same thing as with JSON. And that's very different, for instance, from XC, which you usually would want to use together with a schema description to get compact representation. This compactness thing is secondary to implementation compactness, so simplicity was more important to us than getting the last bit of efficiency out of it. Our main two target areas were constrained nodes, those IoT things, light switches, and high volume applications. So applications where you don't really want to throw a lot of code complexity at consuming or producing the data. This is not HDF5 or something like that. It's not optimized for sending around terabyte-sized databases. But still, you might have high-volume applications where you are sending around lots of, for instance, sensor measurements, and you want to do this in an efficient way. We wanted to support all JSON data types with a defined conversion to and from JSON. And finally, we wanted the format to be extensible. So we are taking a different stance here from JSON, which is deliberately not trying to be extensible. But we think protocol evolution usually requires some extensibility. So pretty much 2 years ago, we finally got an RFC out of that. And people since have actually started implementing that. And there is a website called Cbor.io that actually collects information about what's out there in the implementation space. Okay, so let's talk a little bit about how it works. Now, if I was telling you how JSON works, I would probably use these wonderful racetrack diagrams, syntax diagrams, and so on. But of course, Cbor is binary. So Cbor instance looks like this. Again, the point was to have a binary interchange format. This, by the way, is a table out of RFC 7049 that shows this piece of data in various formats. We actually now also have RFC 731 in that table, which is interesting. Very early RFC that got most of the things right, more so than what has come in between. Anyway, so this is how things look like. Now, if you look more closely, a data item has an initial byte that tells you what it is. And this initial byte is divided into a 3-bit field and a 5-bit field. So the 3-bit field tells you which of these 8 major types you are having. And the other 5 bits tell you something like length information, or if it's just an integer, it might be the integer. So the major types are unsigned, 0 or positive, and negative integers, byte strings, this is the binary data I was talking about, text strings, and text in 2015 means UTF-8, arrays, yes?
Unsigned and negative shouldn't be unsigned and signed.
That would have been one way of doing things, but we decided we would have all positive and 0 numbers in the unsigned major type and all negative integers in the other side. If you know protocol buffers, they have this interesting thing called zigzag encoding. And this is essentially a way to do zigzag encoding without having to shift around the data. So we put the least significant bit of the zigzag encoding into the major type, and the rest is in the data field. So we have arrays, we have maps, we have something called tags. I'll get to this in a minute. And the simple types like booleans, null, and also the floating point values. So this is IEEE 754 floating point values. So what do we do with these 5 bits? If those 5 bits are a value between 0 and 23, it's an immediate value. So for instance, encoding the number 0 gives you a byte with a 0 in the major type and a 0 in the immediate value, and that's all you need for that. And values between 24 and 27 mean that a few more bytes follow, 1, 2, 4, and 8. There are some reserved values, and finally we have a streaming mechanism where if you don't know how many data you will have, this indicates there will be a terminator at the end of the sequence of data items. Yeah, so this, the immediate value, or the 1, 2, 4, and 8 bytes value that follow, generates an unsigned integer. And for major type 0 and 1, that is the integer, either directly or in one's complement. For 7, this is an enumeration type for things like true, false, null, or undefined. Or it might actually be the IEEE 754 representation of a floating point number. For types 2 and 3, it's the length. For types, length in bytes. For types 4 and 5, it's a count in items or item pairs for maps. Or it might be a tag value. Let's come to that in a minute. So the major type 7 is doing these false, true, null, undef values. And we have an IANA registry if we ever need more of them. So far we haven't. And if we are using the values for 2 bytes, 4 bytes, or 8 bytes, actually the value in there is a half, a single, or a double floating point. And finally, tags. That's an interesting idea. So how do we make this format extensible? We defined one major type which allows you to associate a number with a value. And those numbers might, well, these are registered values, and they tell you what that value actually is. So for instance, number 0 means the value is a text string that is structured according to ISO 8601 in the RFC 3339 form. 1 means this is a Unix time, a number of seconds relative to 1970 January 1st. We have big nums, we have decimal fractions, big floats, and a few other things that not everybody needs, but that are useful to have predefined if you need them. And anyone can go ahead and register a tag. The good numbers, the short numbers, require a little bit higher level of effort. But we have enough tags that we will be able to register a few of them. So the Perl community, for instance, have immediately picked this up and done a few tags for Perl-specific things like the Perl reference. If you express 22098 in binary, it's RV reference value, which is what Perl people think is exactly the right thing this tag should be. So tags can be defined for specific applications, and we might want to define a few more of these more general purpose tags here. So for instance, ASM1 object identifiers, tagged arrays, like you have in JavaScript. These are examples for things we might be defining as generic tags. So this means, well, you probably have to digest this slide here in a little bit more time or read the equivalent table in RFC 7049. But a 0 is represented as 0, a 1 as 1, a 23 as 17 hex, and a 24 as 18 hex, because, well, the 24 is the first one that doesn't fit into the immediate value in the first byte. So we use a 1 byte extension and write the 18 in there. And 100 is 1864, and 1000 is 1903E8, and the million is this. It's pretty straightforward, and it's very easy to decode. Now, at some point, we are leaving the 64-bit space, and then we are going to big numbers, which actually contain a tag. C2 means C is 6 multiplied by 2. So it's a tag with the value 2, and this is the byte string that represents that value. These are negative numbers, floating points, infinity, nan, minus infinity. These are all defined in IEEE 754, so it's easy to transport them in Cbor. There's no way to write them in JSON. False, true, and null are these simple types. And then we have hex strings, text strings, and arrays and maps. Now, the interesting thing about maps is you can use any data type as a map key, not like in JSON where you only have strings. So this is how it works. Again, I could talk hours about that, but I think it should be obvious. There really is not more to it. So you could implement it from those 3 slides. So how do you work with it? First of all, if you just want to play around with it, there is a Cbor playground called cbor.me. And this essentially is 2 fields where you can either put in something that looks like JSON or put in bytes and press these conversion arrows, and it will convert between one or the other representation. So this is for playing around. Now, the thing here looks like JSON, but it's not limited to JSON. We have defined a diagnostic notation for Cbor. So we have a common way of to talk about Cbor values in text form. So we can represent binary strings and tags and so on in this diagnostic notation format defined in section 6 of the RFC. Okay, if you want to do more than playing around with it, you probably want an implementation. There are a couple more than 25 implementations right now for a couple of languages like JavaScript, PHP, Go, Rust. The Rust community has been particularly emphatic in picking up Cbor. I have no idea why. Lua, Python, Perl, Ruby, Erlang, and Elixir, Haskell, C#, Java, C, C++, and D. Any of your favorite programming languages that's missing? Okay. Pardon me? Well, that's Java. So if you need it on the Java virtual machine, you use the Java implementation and just link it to whatever you need on top of it. It's just a one call. Can't quite see this, but yeah, go to that side. Lisp, yeah. Somebody has to do a Lisp implementation. It's probably going to be one line in this first thing. Okay, so this is, if you are using it like JSON, that's really all you need to know because it will just work. Now, when we write text-based specifications, we have something called ABNF that allows us to write in a slightly more formal way what pieces of text are actually meant here. And actually, if you look into the history of the RFCs, The first RFC that uses a form of BNF is RFC 40 from 1969, I think. That has a very long history. In the IETF, we always have described text-based protocols using something like BNF. So we thought, is there maybe something like a BNF for JSON-like data models? And of course, there's a ton of proposals how to do schema languages from JSON. You could use one of those schema languages, and it would also probably do the same thing. But we try to limit this to essentially the function of ABNF. And we actually copied the syntax of ABNF, so it looks relatively similar. But the theory behind it is really the theory behind RelaxNG. So if you know what RelaxNG is, you will feel at home very quickly. There's another proposal called JSON Content Rules, where we stole the rest of the great ideas. So very little of this is innovation, but I think we have put it together quite nicely, and we now have something called a Cbor data definition language. That has been stable for a year or so. We're still adding a few things to it where we learn from the actual specification work going on in CDDL that we want to make a few additions. There also is a tool available. This tool is user-friendly, but only to the users that it likes. Well, it sometimes is a little bit verbose in its error messages. But the main use of this tool is either to generate an example instance. So you have a CDDL specification, and it's just going to generate a random instance that is conforming to that. That can be very enlightening. There's something called ABNF gen if you are writing ABNF that does the same thing. Or you have a way to check an instance against the definition. And that's what we use for writing specifications. We want to know whether the examples we have in the document are conforming. So this is an example how a large part of RFC 7071 would have looked in CDDL. That's actually a JSON spec, but because JSON is a subset of Cbor, of course CDDL can describe JSON documents as well. So a reputation object is a map with two keys, application and reputons, where application is a text value and reputons is an array of 0 or more reputons. And the reputon is a map that has a rater, which is a text, an assertion that it is a text, a rated that it is a text, a rating, which, well, okay, we took a little liberty here, is a float 16, assuming that you don't need a lot of accuracy on that rating. And then it has a number of optional components: confidence, normal rating, sample size is an unsigned integer, generated is an unsigned integer, expires is an unsigned integer, and then it has some extensibility, so you can go ahead and define additional entries for that map. So that's pages, I don't know, 5 pages out of that RFC. So that is retroactive. We have looked at 7071 as an example of a document that has a not completely trivial JSON representation, and it takes days to read the description, and it takes 5 minutes to understand this stuff. And for new development, we have an example here, which is GRASP. GRASP is the generic autonomic signaling protocol used in autonomic management of systems. And the GRASP people for once have decided not to invent another TLV for this. That would, of course, be the natural thing, to define another TLV, but they have decided to just use Cbor. And so, for instance, a GRASP message is an array with 3 elements: a message type, a session ID, and 0 or more options. So actually, it's not 3 elements, it's 2 to any number of elements. And the message type is 123. The session ID is value up to 16 million. And options are defined like this. So waiting time option is one of the options. That is actually an array containing the awaiting value and the waiting time, which is a number in milliseconds. So it's pretty straightforward. It looks a lot like ABNF, but it's the square brackets, of course, don't mean optional here, but they mean array as in JSON. Okay, last slide. Where do you go from here? Well, first of all, you go to RFC 7049. Then maybe you go to cbor.io. You might want to subscribe to the Cbor mailing list, which is relatively quiet, but maybe a good way to find people to talk to. The CDDL document is not in RFC yet because we still want to learn from specification efforts, but we expect to move it forward to a working group and then to standards track document next year. And finally, the edu team has asked me for all of you to go to this place here and tell us how good this lightning tutorial was. Questions? Thank you.
那原来走。